So I'm going to go over the detailed function of the timed table-driven feed VI. This VI controls 4 channels of a Sartorius benchtop fermenter, and the function of it is to have an open-loop table-driven feed where there are tables that we load in CSV format that contain time values and pump speed values. And the idea of this VI is to step through the pump speed as the elapsed time progresses. Now, these tables are developed by process engineers based on their understanding of the process that we're trying to implement. And since it's completely open loop, many times things don't go exactly as planned. So the VI has features that allow us to alter the way that we're running the pump dynamically while we're running. And we have several different ways of doing this in the VI. The simplest one is we simply can take manual control of the speed ourselves and ignore what's in the table. The second method is that we have a multiplier, which is a scaling factor, which means if the process is running a bit slower or a bit faster than anticipated, we can basically change the multiplier for the speed so that, for example, we could put in 1.5 and the pump would run 1.5 times faster than the value in the table. Lastly, what we can do is we can actually load a completely new feed table while we're running, and we can either reset the elapsed time and start from the beginning of this new table, or we could jump into this table at the elapsed time that we're currently at. We can also use a combination of these different methods to deal with a running system. The idea here is to give us enough flexibility that in complete open loop mode that the users can have the maximum flexibility of altering the feed tables and without having to stop and restart the entire control process. Now with this, we're going to jump straight to the block diagram. Now again, we've already gone over the basic operation of this, and that there's a outer timed loop that runs forever until a user presses a stop button, which ceases the operation of the program. Inside of this, executing at a speed of generally once per second, we basically read the individual channel controls and then apply the control information along with the current status fed back from the running operation to the actual logic that's implemented here in this big box here. Now I'll be going through this one phase at a time, and what we'll do is we'll follow LabVIEW's execution order, which is generally left to right. And so what we'll do here is we'll start with the enable logic. Now what we're doing here is this is a for loop, so we have an array of controls, of channel controls that come in. This is peeled off in a control loop, in a for loop into 4 independent iterations, basically 4 independent controls for the channels. There's a global enable and then a local channel enable. And so what happens is, in order for the channel to be active, both the local channel enable and the global enable must be true, at which point we then choose the true case and actually do something. For completeness here, if it's not enabled, the only thing that we do is we update some status to ensure that we know that this is a disabled channel. So now we've gone over the enable, and I'll go over this basically from top to bottom. The most simple thing here is the logic here at the very top, which is the manual override logic. Now I'm going to take a quick diversion here to talk about some of this stuff in a little more detail. One of the things you'll notice is the wires that connect these various logical elements together. And we have an OR gate here, a Boolean OR gate, we have a Boolean NOT, we have a floating point select. And the way you tell the difference between these things is, notice the orange wire color. This wire color denotes a floating point. The green wire color denotes a Boolean, which is simply a true or false. And what you'll also see is in other places there are blue wires. These blue wires denote an integer. Now, if you have complex data types, such as clusters or arrays, if a cluster will always come out as this sort of pink dashed line. An array will come up with a fatter than usual line. For example, this is a floating point array that's being indexed, and this is a single floating point value coming out. Sometimes when LabVIEW has to do conversions between types, you'll see a little red dot or a red triangle on the logical element that basically says, well, in this case we're taking a integer, which is blue, and we're changing it to a floating point to match the other input. So now let's get back to the actual function here. So on the channel control we have something called manual speed. And we also have something called manual feed override that comes from a different control. These are both clusters, and so what we're doing is we're peeling off the individual items. So what we're doing here is we're going to pull off the manual speed, and we also look at both the stop and the run button of the manual feed override. What happens here now is that we're going to look to see if either of these buttons have been pressed, either stop or run. And if either stop or run is pressed, we're going to set this output here true, which will go down here and influence what value the manual or the calculated will be passed on to the actual pump and our feedback status. But let's go back here now. So now what happens here is if stop is 1 or true, this will be false. And what we will do here is we will then take the false branch, meaning we will put the 0 into the manual speed. If stop is not true, meaning it's false, then we will pick the manual speed and pass it through. So the output here is either the value of manual speed or 0, depending on how these guys are set. Now note here that stop will take precedence over run. So if both stop and run are selected at the same time, it will stop. Now following down here, we've got yet another selection, and we touched upon that before. Basically, if either stop or run has been selected, that means that we are in manual mode and not in automatic mode. The automatic mode comes in on this branch here. The manual speed comes in here. And so what will happen then is if we are in manual mode, the manual flows through and goes to both the pump speed that we remember and down to the VI that talks to the Sartorius software, which in turn will actually control the physical pump motor. So that's about it for the manual override. So let's back off now, and we'll now look at what happens when we initialize our program. So basically, the first time through our execution loop, of course, the status is initialized with a constant. And the constant basically says everything is disabled. And then what happens is we flow through here and we basically say, yes, we are disenable is false. So this becomes false here. We execute this pane. And what this pane does here is it initializes both the elapsed time, which of course is now going to come through as 0 is defined here. In fact, let me put on context help so we can hover over. Oh, come on. Hover over the whole thing. And we can see, of course, elapsed time is set to 0. In fact, what you see here is you see basically a stack of values, and that corresponds, let me move this over, stack of values in the constant corresponds to what's listed here in the structure itself. So the elapsed time is initialized as 0. We have a table index of 0, and we do have a feed table location that we're pulling in as well, and this is from the channel control. We have some time information that hasn't been initialized yet, but of course we're not using this yet, so it doesn't matter if it's nonsensical. Importantly, also, we have a pump tag name that then defines where we're actually, what tag variable in the Sartorius software we're going to be writing. So in here, what happens is that the feed table location goes into two sub-VIs. And this sub-VI here, let me turn my help back on. This sub-VI, we basically have inputs. We have a column, we have a file path, and a column to select that we're wiring up, and we're leaving the format string default. So what's happening here is that we are reading the table file, and we are pulling out the values for pump speed and for elapsed time. And then we are loading these into two arrays, the speed array and the time array. And what we'll be doing later on is we will be using these two arrays to set the pump speed and check the time when we have to move through the arrays, basically element by element. Now over here, what we're doing is, now our table index, as we know, is 0. This pulls over here, comes up to this guy here. What that is an index array. So what we're doing is we're pulling in the pump speed array comes in here, and we are taking the first element, which is the 0th element of the array, and we will then be selecting that and peeling that off and sending it out for further processing. For completeness here, we have table index, and the table index here is going to be 0, and regardless of the value of the reset elapsed time checkbox, 0 will be passing through. And so we wind up with a table index of 0. The pump speed is going to be whatever comes out here. Oh, and I got ahead of myself. What comes out of the table is a floating point number that tells us what speed the pump should go at. And we have the multiplier here, which is by default 1. And this is where we can adjust the speed of the pump based on a constant that the user puts in. So I made the example before, if we had 1.5, it would multiply 1.5, what was coming out by 1.5. If we are not in manual mode, basically if this is false, neither of these guys selected, we then pass our value through here, which goes to our status and off to the pump itself. Now in the next iteration, we transition to what I call run mode. And run mode is dealt with a little bit differently. And run mode, whoops, that's false. Come on, let's go to true. Now during run mode, what we're going to be doing is we're going to be working off the arrays that we read in before. We're going to be incrementing our time as necessary, and then we'll be switching through the array. So let's start at the top here. So we bring in the elapsed time, and we add 1 to it. So you see what our elapsed time really is doing is basically counting iterations. Normally what we have is we have our program set up so that it executes at a once per second basis, and so elapsed time and seconds are one and the same. The elapsed time here is passed out and kept in status for use next time. It's also directed downward into some other logic here. Now, the other logic, let's take a look at it. This is where we're going to be checking table indices. So the first thing that we're going to do is we read the table index that we calculated on the last iteration and basically pass it on to both index array units. So we pull out the value of the speed and the time that's correct for the point at which we are. And then what we're going to do is we're going to do some tests to see if we should increment our array index or not based on the passage of time. And so what we're going to do here is we're going to compare right here the current elapsed time, which of course is counting up at each iteration, with the value of time that's stored in the table that we read in from a file. And as long as the value we read in from the file is greater than our current value, we're going to select, our output will be true. we will select the upper line here, which means that the table index passes through unchanged. Now, if this is false, we're going to pick up the output of this lower logic here. This lower logic is a little bit unobvious. It's not very complicated, but it's a little unobvious. The table index here is being incremented by 1. And generally, this will flow through. And so if the table time is not greater than the elapsed time, then we're just going to pick up the index plus 1. But we do some other checking here. And this checking really is, as this comment shows here, is looking for the end of the table. And what we do here is we basically, now that we've read in the time value at this point in the program, we can see how many entries there are in the time table. Now, we assume that the speed and time tables will be, they'll be of this exact same size. But at this point, we basically read off the time, and we get a number here that says how big that array is. And so what we're going to do is we're going to compare this with the actual table index that we're on. And what this comparison is going to do is it's going to see if we're at the end of the table. Now, there's a subtlety here in the way that LabVIEW works, and that LabVIEW uses the convention of the C programming language in that array entries are indexed zero-based, which means the first entry in the array is the 0th entry in the array. If you ask for the array size, however, you get something that's 1-based. And so the idea is if you have a table that's, for example, 20 entries long, the output of the table size will be 20, but the indices of that array are numbered 0 to 19. And so essentially what we have to make sure of is that in this case we're saying if this output is false, then everything is cool and we're not at the end of the table. But if we are at the end of the table, meaning we're at index 19 in the example of a table that's 20 long, well then we're not going to select the incremented value index here because we'd run off the end of the table. And so then we basically do not increment the index and basically stall. The idea here is that if the program runs for a very long period of time and runs off the end of the table, what happens is that the program simply stops at the last valid value in the array and pumps at that speed forever. Now, let me go through. It's pretty obvious how enabling manual speed control and changing the multiplier work, but let's go through what happens if we want to load a new table. If things have gotten bad enough so that we really want to put in a modified feed table based on the fact that things are not going as planned, the way to do this actually is to temporarily disable the channel. And there's some subtleties in this. Now, one of the things that you need to, one trick to know is that notice if we disable the processing, nothing is being written to the Sartorius. So what will happen is if you disable processing in a channel, the pump won't stop. It'll keep going at whatever it was last commanded to. And so normally what one would do if you want to disable the channel is you'll first put it in manual control and set it to 0. And then at that point, of course, the pump will stop. Now, if you want to reload the table on the fly, what you can do is you can either just simply quickly disable the local channel enable, which now stops the processing, but the pump is still running at whatever it was running at before. Or you set the pump to a particular speed using the manual override and then disable the channel. Now, when you re-enable the channel, What's happened here, of course, after you've disabled it is put false into the enable status. So if you re-enable the channel again, false will be read back through this through the shift register, because that's where the status is circulating, and then it will re-execute the initialization, which means it will reload the arrays from the from your file. Now here is actually where the reset elapsed time unit control becomes relevant, because if you put a new file in there, you could elect to either have the system carry on at the same time offset it was before, and you could do this, like, for example, say you wanted to keep the time breaks the same and just change the speed. Well, then you wouldn't change the time values, you just change the speed values, reload it, and it would pick up exactly where it left off. Other times you might want to replace the entire table and you just want to have everything start over from scratch, at which point you would then have this set to true. You'd select the reset and elapsed time, and then what it would do is it would force a 0 into the next offset, right? It would still pick the initial offset for the speed, but then 1 second later, it would transition to what has been reinitialized. So I guess I should talk a little bit. That was a little tricky. Bottom line is the table index note. It's pulled off before we actually would set it to 0, but we set 0 into the status, which circulates around. Now, it maybe could have been done a little bit better than that, but in our case, usually 1 second doesn't matter in the slightest, and because the pump obviously doesn't respond that quickly. So at this point, we've gone over the operation for both run mode and for initialization, the override, and obviously the multiplier here. Now, perhaps in a later video, I can go over the detail operation of the read spreadsheet. As you can see, this is a reason. It's not absolutely trivial, so it takes a few minutes to walk through. This guy here literally calls a system function. It's the only thing that VI does, and this thing here can be configured. All the values that go in here basically are pulled out of the Sartorius Programmer's Reference Manual, because it has to do with their specific system DLL. It's called the Dynamic Link Library, and we're calling the appropriate routine and having appropriate parameters and things. Bottom line is all this information is gleaned from the Sartorius Programmer's Reference Guide. So at this point, we've gone over the detail operation, and not much else to say on this VI.